Okay, so my name is Frank Wirtwein. I'm a particle physicist in the physics department here, and I'm going to talk about big data at the Large Hadron Collider. This is a few slides out of a presentation I gave a couple of weeks ago at HPCast 21, and I put the URL here in case people want to know more. And I'm going to talk about big data at the Large Hadron Collider, starting with the science and sort of moving towards more technical subjects. So the science, after the Nobel Prize in Physics this year being given to the Higgs discovery, where I'm talking mostly beyond. And the next big thing beyond Higgs is the dark universe. And the issue here is that the universe as we know it is a rather dark place in that 71% of the matter energy content is dark energy, and we have no freaking clear idea what this is. Basically, it's actually not even a conceptual explanatory model that would be workable as a hypothesis in a satisfactory way. Then there is 24% of the matter is dark matter. There we have very good ideas. We have actual real hypotheses that you can hunt for and search for in the data with experiments, so that's good. And then there's all of 5% of the universe that we actually know what it is. And my objective is to go from this 5% of known stuff to add the next 24% and make that known stuff. And how do I do this? Whoops. If you want to, as an experimentalist who works in a lab, I want to create the stuff that I want to study, right? And so I have to have a lab where I can create dark matter. My lab that I create dark matter in, or try to, is the Large Hadron Collider. And what you see here is an aerial view of Geneva. This is the Lake Geneva, this is the Mont Blanc, and this here is the Large Hadron Collider that you see. It's a tunnel underground where, that is 27 kilometers long, where we collide protons on protons. In fact, we collide beams of protons on the beams of protons. A beam of protons about this long. It is hair thin. It's about 30 micron in diameter, and we collide these every 25 nanoseconds. So stepping back for a second, how do we do our science? People like to say that we create a big bang in the laboratory. Okay, fine, what does that actually mean? It means that we gain insight by colliding protons at the highest energies possible, and when we collide these protons, we measure, crudely speaking, three things. We measure the rate of production of certain phenomena, we measure the rate of decay of certain particles, and we measure the masses and lifetimes of the particles that we produce. And by measuring these kinds of phenomena, we then deduce the entire spectroscopy of everything that exists as far as elementary particles are concerned, and we derive the dynamics, the forces between these particles, and so forth. And doing this kind of science, progress is made by higher energy beams and brighter beams. In other words, if I can make beams that have higher intensity, I can study rare phenomena because I get more collisions. It's that simple. If I can get beams at higher energy, I can produce particles that have higher mass and therefore push the envelope towards new phenomena. And that's sort of how you make progress in this kind of science. Then you need an experiment to actually do take the data with. And our experiment, I think the easiest way to think of our experiment is think of an 80 million pixel camera. And now imagine that this 80 million pixel camera takes pictures every 25 nanoseconds. That's our experiment. Now, if you multiply these two numbers together, assume 4 bytes per channel for digitization, you end up with 10 petabytes per second of information, and that is, of course, unmanageable. It's silly, it's stupid. You don't write that to tape. And so what the first thing we do is we do zero suppression. All the channels that are below threshold don't get read out. The second thing we do, we only record collisions that are interesting. We record about 1 out of 100,000 collisions. All the other collisions is the science from my grandfather or my father or whatever, people long before me. And then this is big science, and so you end up with about 2,000 scientists across 100 institutions in 40 countries that collaboratively run this experiment, collaboratively take this data, and then competitively analyze the data. And to give you a sense of the kind of science that comes out of this, I'm showing you here just one example. On the y-axis here is the double differential cross-section distribution, and on the x-axis is JetPT. And what you see is, you see data points, right? And the data points are data points that are measured, and then you see a line across on it. That's a theoretical prediction. And our single experiment, one experiment, measures nature to 15 orders of magnitude and agrees to the theoretical explanation to 15 orders of magnitude, at least on a log scale. And that's sort of, every time I give this talk, I challenge people to send me per email other examples in science that have this kind of dynamic range. And the only one that I've heard so far is Hubble telescope that apparently has a similar kind of dynamic range, because from large-scale clusters to single stars. And then down here, somewhere down here is where I'm hoping to find dark matter or produce dark matter under this mountain of data. So the basic technological problem is finding the needle in the haystack. And so how do I do this? How do I do my science? What do I do actually personally? I take the produced data set of CMS, which is a few tens of petabytes, and I don't actually know how much it is because it is lots of different types of simulation, and then the data from the actual experiment, and I haven't bothered to add it all up. I don't know what it is, how much. Then my group distilled this into a data set that's about 400 terabytes, and that I know how much it is because I pay for the disk space to host it in Meyer Hall. And so we have a 400 terabyte data set sitting on our disks in Meyer Hall, and we bang on it with our cluster. And using this cluster, our students and postdocs distill data further to anywhere between 1 and 100 gigabyte or so of refined data. What they do is they select the needles out of the haystack, and they refine the format to reduce the size of the events by an order of magnitude or a little more. And then that data then becomes, they extract onto their desktops or whatever and analyze on a day-by-day basis. And then they go back when they realize, oh shit, I forgot something. I should have written this out as well, and then go back and distill again. And we've done this now for 3 years, written 20 scientific papers out of this, and the accelerator is down right now for refurbishing, and it's coming back up in 2015, and then we're going to do it all over again at roughly 1.6 times the energy and roughly 4 times the data volume, because the rate at which we're going to write out data the next time round is increased by that factor. And that basically sums it up, and I had one last slide, and that's about tools. I have a little bit of a split personality as a scientist because I do my science searching for dark matter, trying to understand dark matter, and then I build tools because I'm an experimentalist. I'm a tool builder, and my tools I offer to other people. And so if you care to use my tools, send me an email. Thank you very much.
Great. Thank you, Frank. We have a minute for questions.
So coming from biology background, this collaborative data generation and then competitive data analysis is actually the exact opposite of what we do, right? It's biologists generate their little data sets and they sit on them and try to chew on them by themselves, right? And then only after the paper has come out do they share the result. So what you're doing is you're sharing your data with everyone that wants to look at it and then trying to extract the best morsel out of it, right? So what are the constraints that make that a good solution for physics but not for biology?
It's the cost of the experiment. Given that the laboratory, this 27-kilometer collider and the 80 megapixel camera that takes pixels every 25 nanoseconds, takes pictures every 25 nanoseconds, making that work requires this collaboration of 2,000 people across 40 countries. There's just no way in hell to make this work without that many people and that much effort and funding from 40 different funding agencies, ultimately. And so you're stuck with this large juggernaut of collaboration, and that's the answer.
Thank you.
It's not by choice.
Yeah.
No, it's, I mean, look, you got to do what you got to do.
Go ahead, Julia.
From Geneva to here in different locations.
So we built when we started the serious preparation phase in around 2004. The short answer is via the internet. So there is we have a semi-closed set of networks that connect Geneva to 7 primary processing centers and archival centers in the world. One of them in the US, which is a Fermi National Lab. And then we use a combination of ESNet, which is the DOE's network, and Internet 2, which is everybody else's research network. And that combination of those 2 networks are then used to bring it to places like San Diego. There is about, the kind of infrastructure that I have in my lab is 1 of 40 for my experiment worldwide. Mine is probably, I'd say, one of the top 10 largest, but to 0th order, there are these centers that everybody can use. I run this center as a facility for the entire collaboration. So everybody in the collaboration can send jobs to me, but the data goes to these centers. And then when my group runs at one of these centers worldwide, whichever one happens to have the data that we want, then the output files that we produce get sent back via grid FTP to here, to San Diego. And that then has its usual things, that sending large files over the Atlantic, timeouts, and it's complicated.
Thank you so much.
Thank you.